In this video, we're going to talk about solutions. Solutions is something that we've been using all the time in our labs. We just haven't really gone in depth about this topic. These are your learning targets. Now, a solution is a homogeneous mixture where a solute is dissolved in a solvent. So there are two parts to a solution. There's the solute, that is a substance that's being dissolved. It's usually the one that is in lesser amount, and it's usually a solid, but not always. There are liquid solutes, gas solutes, and you'll see that in the next slide that I turn to. But in our class, we're usually dealing with solid solutes. The other part of the solution is the solvent. The solvent is the one usually in greater amount. In our class, it's usually a liquid. In fact, it's usually water, but again, there are different types of solvents as well. So here you'll see the different types of solutions. There are different solutes and different solvents. There are gas solutions, liquid solutions, solid solutions. So for example, air, you know that it's not just pure oxygen, right? We have a mixture of gases in the air, and so we say that there's a gas solute dissolved in a gas solvent, and that's how we get our solution, air, okay? Other things like humidity, we have liquid solute in a gas solvent, that's how we get humid air. Liquid solutions are the ones that you are probably most exposed to, like carbonated drinks, salt water, household cleaning products. A lot of the acids and bases from our class, those are liquid solutions. And solid solutions are like sterling silver, your dental fillings, those are solid solutions as well. So again, different solutes and different solvents to make different types of solutions. Now, these might be new words for you guys. When we say that something is soluble, we're talking about a solute that can be dissolved in a given solvent. So for example, salt can dissolve in water. We say that that's soluble. When the solute cannot be dissolved, we say that it's insoluble. Okay, and you guys probably remember the chart that we used, the solubility chart that we used, I think a couple units ago. We're actually coming back to that today. And then lastly, we have immiscible. When a liquid solute does not dissolve in a liquid solvent, like for example oil and water, we say that it's immiscible. There are three types of solutions: saturated solution, unsaturated solution, and supersaturated solution. A saturated solution contains the maximum amount of dissolved solute for a given amount of solvent at a specific temperature and pressure. So I like to use the example of Kool-Aid, right? You have your Kool-Aid powder and you dissolve it into water. Now, everyone has their own definitions of the perfect Kool-Aid. Some like it a little bit sweeter, some a little bit less sweet. But whatever that perfect Kool-Aid is for you, that is the saturated solution, right? So in a perfect Kool-Aid, it won't be too watery, and you won't have so much where you have solid that's not dissolving, right? So it's the maximum amount of dissolved solute for a given amount of solvent. Unsaturated solution means it contains less dissolved solute for a given temperature and pressure than a saturated solution, meaning more solute can be dissolved. So this might be your watered down Kool-Aid, right? You can keep dissolving and the Kool-Aid mixture will continue to dissolve, right? You won't see any solid in your pitcher of water, right? In your pitcher of Kool-Aid. Supersaturated solution means that it contains more dissolved solute for a given temperature and pressure than a saturated solution. So let's say you accidentally dumped a whole can of Kool-Aid powder into your pitcher of water. What are you going to see happening? What is it going to taste like? First of all, it'll taste super, super sweet, right? Second of all, you'll see that everything, all the powder won't dissolve. it'll just probably sink to the bottom. Some of it will dissolve for sure, but most of it will just sink to the bottom of the pitcher and will just never dissolve, right? So that is a supersaturated solution. Next, we're going to talk about molarity. Now, if you remember, we actually talked about this with our collision theory. We talked about the formula then, and we're going to talk about it again right now. But before we get there, let's first talk about the word concentration. Okay? Now, when you hear the word concentration, we use it when we talk about molarity, but concentration itself actually is talking about like a qualitative value. So, and it's not numerical. So concentration, the word concentration just gives us an idea of how much solute is dissolved. So there's two things that we can say with concentration. We can say that this is dilute, or that this solution is concentrated. So when you guys already know what dilute means, right? Dilute means that there's too much water, right? So only a little solute is dissolved for dilute solutions. And concentrated solutions means that there's a lot of solute that's dissolved, right? So even if you look at this picture on the left side here, the blue represents the solute and the pink represents the solvent, or the bigger circle represents the solute and the smaller one represents the solvent. And you'll see that for a concentrated solution, there are a lot more solute particles in there, right? And for a dilute, you see that there's less solute particles in the solution, okay? So concentration is just like a qualitative measurement, okay? Whereas molarity is quantitative, and we talked about molarity as moles of solute divided by liters of solution, moles divided by liters, okay? So let's take a look at our first example, which is going to look similar to a previous problem that we did earlier on in the year. Determine the concentration if 4.67 moles of lithium sulfite dissolved to make 2.04 liters of solution. So for this problem, you're simply going to just plug it in and solve, okay? So determine the concentration. Concentration is molarity. Again, you might see these two words used, okay, interchangeably. So concentration is molarity, and so you just plug it in, divide, solve, 2.29 moles per liter. So remember that unit, moles per liter, is big M. Okay, so big M represents molarity, and big M is moles over liter, moles per liter. Okay, so you can write either unit, but you'll see a lot of our solutions in class with this value here, 2.29 big M, 2.29 molar solution. Second problem, determine the molarity if 4.783 grams of sodium chloride dissolved to make 10.00 liters of solution. Now, you see the first thing here, it says grams, right? And if you look back at our formula, you can't just do grams per liter, right? What do you have to do? You got to convert the grams to moles. Now, I'm going to show you how to set this up in the fence. Yes, you can simply just convert it and plug it back into that formula that you see on the screen, but for my honor students, and especially for those of you guys who are going into AP chemistry, you guys got to know how to set it up like the fence, okay? So remember the fence, it's just all about units, okay? So you're trying to put the units in the right place. So we're going to start with 4.783 grams of sodium chloride. What's your next step? You're going to bring down grams of sodium chloride. And where do you think you're going to go? You're going to go to moles, right? Because even here you see that you have to go to moles in order to find the molarity, right? So let's fill in this fence here. 1 mole of sodium chloride is equal to, what's the molar mass of sodium chloride? I'm going to pause the video here so that you can calculate it and then unpause. It's 58.44 grams of sodium chloride, right? So our like units cancel out, and what are we left right now? We're left with moles, right? So again, yes, from here you can just simply plug it back into the formula, but I'm going to just keep using the fence, and especially, again, just to emphasize, you guys who are going to AP chemistry, make sure that you guys are going to set it up like the fence, okay? So I have another fence, and this time I'm going to write 10.00 liters on the bottom, right? Yeah, remember the fence is all about writing your units down, canceling when you need to, but also you don't, when you do your fence across the fence, you don't, it does not have to be the same exact unit, right? We can even manipulate it so that we end up with moles over liters, right? Moles per liter, and that's how we get the molarity. So if I do this, on top I'll get moles, and on the bottom I'll get liters, right? Because my grams canceled out. So we're going to multiply and divide, and what do you get? You get 8.184 times 10 to the negative 3 molar solution, okay? And that's with significant digits, all right? Last one, Cyclops needed to make 500 milliliters of a 3.5 molar solution of sodium hydroxide. Explain how he would prepare the solution. Now, before we could even explain how Cyclops can make this solution, we got to first solve for something, right? So we're going to set it up in our formula, and it looks something like that. And what do you notice about this that is different from the formula? If you said that the volume is milliliters and not liters, you are absolutely correct. So we are going to have to convert our milliliters to liters, all right? And so remember that there's 1,000 milliliters in 1 liter, so I'm going to go ahead and rewrite that as 0.5 liters. And if you solve for x, you get 1.75 moles of sodium hydroxide. All right? Well, can we measure that in a lab? No. If you think about it, our balances are not moles. What are our balances? Our balances are grams, right? Or it's in grams, right? So I'm going to go ahead and convert this. And if I really wanted to, I could have just done it like the fence, for the full fence, just like I did in number 2, but I just wanted to explain why I wanted to go to grams, right? So with 1.75 moles, we're going to bring down moles, and we'll write grams on top. I'm going to find the molar mass of sodium hydroxide, and we have 1 mole is 40.00 grams of sodium hydroxide. So how much does Cyclops need to measure out? He needs to measure out 70 grams of sodium hydroxide. So 70 grams sodium hydroxide. I didn't answer the question yet, so I have to explain, right? So Cyclops would dissolve 70 grams of sodium hydroxide into 500 milliliters of water in order to make a 3.5 molar solution of sodium hydroxide. Next, we're going to talk about dilutions. Sometimes we want to change the concentration of a solution because maybe the concentration is too strong. For example, when I get hydrochloric acid from Flynn, it's 12 molar acid, and you guys know that I won't let you guys use 12 molar acid, so I dilute the solution myself. And you guys use concentrations of like 6 molar, 3 molar, 1 molar, 0.75 molarity, and you guys have seen previously that different concentrations will also lead to different reaction times, right? I mean, depending on what kind of solutions we're working with. And so in class, if we were to do a dilution, we would calculate how much we need or what concentration we would dilute to by using this formula here. M1V1 is equal to M2V2. M stands for molarity, V stands for volume. These, the 1 is the initial conditions, and then 2 are the final, okay? So let's take a look at our first problem. What is the final concentration if 50 milliliters of a 2 molar solution is diluted to 500 milliliters? So I want to find M1 and V1. So here we have 2 molar solution at a volume of 50 milliliters, and it is diluted to 500 milliliters, which is our second volume, and we're trying to find the final concentration, right? So this is just simple algebra here. Multiply and divide, and you get a molarity of 0.200 solution, okay? once you determined your answer, I want you to just take a quick second and just think about your final answer. Does it make sense? If you're diluting a solution, your final concentration should be lower than your original concentration, because when you're diluting something, all you're doing is adding water. So does it make sense that your final concentration for problem number 1 is 0.2 when you started with 2 molar solution? Yes, it does. So in this case, you would take, if we were in a lab, you would take 50 milliliters of a 2 molar solution, so you would measure it out, and then you would add enough water until it got to 500 milliliters. And that's how you would make 500 milliliters of a 0.2 molar solution. The key thing here is that you want to make sure that you're pairing up the correct molarity with the correct volume. So this is a common mistake that I see with students, and you just got to make sure that when you're reading it, it usually says something like this: 50 milliliters of a 2 molar solution, and you know that those two will be paired up, okay? The other important thing is you got to figure out, well, are they talking about the final volume and final concentration, or are they talking about the initial volume and initial concentration, okay? Second problem says if you dilute 20 liters of a 3.5 molar solution to make 100 liters of solution, what is the molarity of the new dilute solution? So again, we're going to set it up so that the molarity and the volume are paired up together. So 3.5 molarity times 20 liters is equal to M2 times 100 liters. Multiply and divide, and you get a new molarity of 0.7 molar. Next, we're going to talk about physical properties of solutions. First, we're going to discuss electrolytes. This is probably something that is familiar because we talked about it earlier on in the year. Electrolyte is any substance containing free ions that make the substance electrically conductive. Okay? Ionic compounds, we talked previously, are our strongest electrolytes because there's 100% dissociation in water. Okay, so for example, we have salt, we have solid salt. Okay, think about just your table salt. If you put it in water, what happens to that salt? It's dissociating. Okay, so as it dissolves in water, the ions dissociate. So then you get your sodium ion and your chlorine ion. Remember that dissociation just means separation. Okay, so the ions are separating, and remember, if something is electric conductive, there's got to be a positive, there's got to be a negative side, and that's why ionic compounds are the strongest electrolytes, okay? So for sodium chloride, it breaks up into a sodium ion and chlorine ion, and so we say that 1 mole of sodium chloride dissociates into 2 moles of particles. And we'll talk about this in a couple more slides. If you don't remember how we get this, you might want to go back to your redox notes, because that's where we actually broke up these substances, okay? And so the second example, sodium sulfate. Sodium sulfate can break up into sodium ion and sulfate ion. And there's 2 sodium ions because it's Na2. So in the compound, there's 2 sodiums, so we have to reflect that when we talk about sodium ions, okay? So for there's a total of 3 moles of particles when sodium sulfate dissociates. And again, we'll talk a little bit more about that on a future slide, all right? Covalent compounds are non-electrolytes because they don't dissociate at all. For example, like sugar, it will dissolve in water, but because sugar is not composed of positive and negative ions, when it dissolves, it's not going to dissociate, it's just going to stay as that one sugar molecule. Okay, so this is methanol. Methanol will not separate, it does not dissociate, so there's just 1 mole of methanol there. Okay. So I'm using this PhET simulation just to show you guys what it means by a solution being conductive or not. So here we have salt like sodium chloride, and I'm just going to dump that into the water here. I'm going to take my light bulb and show you that it's conductive. The solution is conductive, okay? So that's how we know that salt is a strong electrolyte, all right? Now, if we were to, let me put this back, change it to sugar, and let's say we put some sugar in there. Okay, a little bit more. Oh, maybe I used all of it. Okay, so if I put this in here, you see that the light bulb doesn't even light up, right? Because again, sugar is not an ionic compound. Remember, ionic, the word ions, right? So sugar is covalent. It's not made up of ions. Yes, it dissolves in water. However, even though it dissolves in water, it does not dissociate into ions. The compound or the molecule does not separate into ions, okay? Now I want to show you this on a micro level. So like for example, sodium chloride, put some sodium chloride in there, and you see that once it hits the water, it separated completely. You have your sodium ions, which are pink, or the smaller ones, and then your chloride ions are the green ones, or the bigger particles, and there's complete separation. So that's complete dissociation, okay? Whereas sugar, so if I dump that in there, you see that there's no separation at all. It stays together, okay? So no separation, no dissociation. All right. Lastly, we're going to talk about colligative properties. Colligative property is the effect of a solute on a pure solvent, which depends upon the number of solute particles in the solution. The more solute there is in the solution, then the greater the effect is going to be. So we're going to talk about three colligative properties. We're going to talk about vapor pressure. We're going to talk about vapor pressure lowering. We're going to talk about freezing point depression, and we're going to talk about boiling point elevation. Okay, first we'll talk about vapor pressure lowering. The vapor pressure of a solution is less than the vapor pressure of a pure solvent. So think about water as your pure solvent, okay? So the vapor pressure of a solution, for example, if I were to add salt to water, because we do that a lot, right? In cooking, we add salt to water when we boil water, usually when we're making pasta, right? So if we were to do that, we are lowering the vapor pressure. So in a solution, solute particles reduce the number of free solvent particles that are able to escape the liquid. So think of it this way. Just think about if you are dissolving salt, then that solute is kind of like making a barrier. It's kind of blocking the water from evaporating. Okay, so that's how you can think of it. It's forming some kind of barrier. It's blocking the water. Okay, it's getting in the way. Okay, so the more salt that there is in the water, then the lower the vapor pressure is going to be. Okay, so for example, 3 moles of glucose dissolved in water produces 3 moles of particles because glucose doesn't dissociate, it's covalent. Okay, while 3 moles of sodium chloride in water produces 6 moles of particles because of the sodium ion and the chlorine ion. If you have 3 moles of sodium chloride, then you're going to make 6 moles total of the ions. Okay. Therefore, the sodium chloride solution will have a lower vapor pressure than the glucose solution. All right. And again, this is going to be a lower vapor pressure than just pure water. All right. The second thing is boiling point elevation. A solution will boil at a higher temperature than the pure solvent. So the example that I like to talk about is, again, boiling water, putting salt into water when you're trying to make pasta. Now, what's the reason you put salt into water when you make pasta? You might have heard that you put salt into water because it makes the water boil faster. Well, that's actually false. And this colligative property, this is telling us why that is false. Okay? We add salt, when we add salt to the water, it's actually increasing the boiling point. Okay, so water boils at 100 degrees Celsius, right? If you add salt to that water, it doesn't boil at 100 degrees Celsius anymore. That salt water, it's going to increase the boiling point. So it might boil at 101.5 degrees Celsius. Okay, I don't know the exact temperature because it's going to depend on how much salt you put in there. But the whole point is that the boiling point of salt water is going to be higher than the boiling point of just pure water. Okay, so what is the reason why we put salt into water for our pasta? That's the only time you can flavor your pasta. That's why we put salt in water, for that. Okay. The third colligative property is the freezing point depression. A solution will solidify, a solution will freeze at a lower temperature than the pure solvent. So the example I like to use with this is, why do we add salt to the roads? Now, a lot of people will say, and if we were in class, you would have said, because it helps melt the ice, or it helps melt the snow. And you would be incorrect. Okay? And this is why. It doesn't melt the snow because it says right here that a solution will freeze at a lower temperature than the pure solvent. The reason why we add salt to our roads in the winter when it's about to snow or when it does snow is so that the overall temperature, the overall outside temperature has to be lower than 0 degrees Celsius. Okay? Think about it. When we have hopes for snow day, right? The weatherman says that it's going to snow. We're looking at, I don't know, like 5 inches of snow or whatever. But what is that other part that we need to consider? Well, what's the temperature going to be like, right? And we're looking for 32 degrees or lower. Why 32 degrees or lower? Because that's when water freezes, right? And so that's what we're looking for. Anything higher than that, then the snow's not going to stick, and we're going to go to school the next day. But so we're looking for 32 degrees. So when the trucks come, not the tow truck, but the snow plows and the trucks with the salt and all that and sand, they come and they put it on the roads. The reason why they do that is because then the outside temperature has to be below 32 degrees in order for the snow or the rain to ice over. Okay? So, the other reason could also be for traction, right? So that our cars aren't slipping everywhere. Okay? So those are the 3 colligative properties when you add a solute to a solvent. So let's take a look at our example. Rank the following from lowest to highest boiling point. This is all 1 molar concentration, so magnesium chloride, sodium chloride, and sucrose. Well, the first thing you need to do is you need to convert these into formulas, because then we can figure out some other pieces of information, like will it dissociate or not, and what will it dissociate into, right? So magnesium chloride. Now, if you forgot all about this, remember we have to consider oxidation numbers, right? So magnesium is +2, chlorine is -1, so we get an overall formula of MgCl2. Sodium chloride, we have Na+1, chlorine -1, so we have NaCl, and sucrose is C12H22O11. Okay, probably don't remember that from bio, so the next thing we need to figure out is, well, will these dissociate? So what does that depend on? It depends on if it's ionic or covalent, right? So magnesium chloride, is that ionic or covalent? That's ionic, so it will dissociate, okay? So what will it dissociate into? In order to answer this question, you have to remember, well, what did we use to make magnesium chloride? So when it dissociates, so when it breaks up, it's going to break up into those same ions, okay? So magnesium is, remember, +2, so we have Mg 2 plus, and chlorine is -1, so we have Cl 1 minus. The next thing we want to do is make sure that our ions match up the number of atoms on our left side, right? So we have 1 magnesium and we have 2 chlorines, okay? So how do we reflect that over here? We have to put a 2 as the coefficient, and that way we have 2 chloride ions, okay? 1 magnesium ion and 2 chloride ions. And so that gives us 3 moles of particles that magnesium chloride dissociates into, okay? Let's take a look at sodium chloride. Sodium chloride, is it ionic or covalent? It's ionic, so we know that it'll dissociate, okay? What will it dissociate into? It'll dissociate into Na+1 and Cl-1, okay? Do we have to put any coefficients in front of our ions? No, because this is just 1 and 1, okay? So sodium chloride, 1 mole of sodium chloride dissociates into 2 moles of particles. Let's take a look at our last one, sucrose. Sucrose, is that ionic or covalent? It's covalent, right? So it will not dissociate. Therefore, it will stay as C12H22O11, and that's only 1 mole of particle. So how can you rank this from lowest to highest boiling point? Knowing that now there's 1 mole of particle and sodium chloride dissociates into 2 moles, magnesium chloride dissociates into 3 moles, how do you know which one will have the lowest and which one will have the highest boiling point? So remember, greater the amount, so greater the number of moles, basically, greater the effect, okay? So they're talking about boiling point, which really they're talking about boiling point elevation, okay? So which one will have the highest boiling point? That's your magnesium chloride, because it's the most amount of particles out of these 3, okay? So sucrose will have your lowest boiling point, and magnesium chloride will have your highest boiling point. And that's it for colligative properties and solutions in this video.